Our last section for this unit will cover neutralizations. A neutralization reaction is a reaction in which an acid and a base in aqueous solution, so they're dissolved in water, react to produce a salt and water. So generically it kind of looks like this. Acid plus base yields salt plus water. Remember, a salt is an ionic compound made up of a cation from a base and an anion from an acid. So it also should be an aqueous salt, so it should remain dissolved in water. As far as the type of reaction this would be, right, you've got two compounds forming two compounds. All neutralization reactions are double replacement reactions. Why? They're going to form water. Okay, so you might remember that from the other unit. Breaking this down further, here's an example. NaOH plus HCl, so NaOH is the base, HCl is the acid, yielding sodium chloride, which is the salt, plus water. So what's really going on? Well, since everything is aqueous, they're all dissolved as ions. The hydrogen ion and the hydroxide ion are going to react to form water, right? Because those are the two parts that would make up a water molecule. The remaining parts form the salt, whatever's left over. So when the hydrogen and oxygen react, what's left over is the sodium and the chloride. Those react to form the salt that would stay dissolved in water. So really, it's almost like nothing happens though, right? Because this is all aqueous, so it all stays dissolved in solution. So in a way, they're kind of spectator ions. So what we want to look at here is something called acid-base titration or neutralization reactions, right, is what they're also called, okay? This is if you have an acid or a base and you want to neutralize it. You want to make it neutral, to have a pH of 7, okay, as long as it's a strong acid and strong base, which is the only thing that we're going to worry about in a general chemistry class. The goal here is to use stoichiometry to determine how much of a particular reactant is needed to neutralize the other reactant. And this process in lab is called titration, okay? So we'll definitely get a chance to do this in the lab together. Definition-wise, this is the method for determining the concentration of a solution by reacting a known volume of that solution with a solution of known concentration. I know that sounds a little confusing, so we're going to try to simplify that out here shortly. Think about this as really stoichiometry with acids and bases. Okay, so here's the general setup of what this looks like in a lab. We have this tall, narrow piece of glass called a burette, okay? It's usually, I don't know, close to maybe a meter tall. It's very thin, and it's got graduations on the side that are very, very precise. Down below is something called the stopcock, and that leads to the nozzle. This lets whatever's filled inside of here flow into the beaker underneath. What we fill this with is a known quantity of base, because we know the volumes, we have the markings on the side, and the known concentration of base. So we know the concentration and we know the volume of the solution in here. Underneath, down below in the beaker, we're going to have a known volume of acid that will be usually pipetted into here. And then we'll have an unknown concentration of that acid. So generally what we're doing with an acid-base titration is trying to figure out what's the concentration of the acid. We will also put an indicator in here to tell us when this reaction is complete. Usually it's something like phenolphthalein, which turns from clear to pink, okay? But the goal is to use the base to drop into the acid, and then we wait until the reaction is done by watching for the indicator. And from that, then we can find the concentration of the acid. So what we can actually do is graph the pH. There's usually like a pH meter too that we can stick into the acid solution underneath, and watch what happens to it over time. Okay, and eventually you reach a point where the pH is going to shoot up very quickly and then level back off, okay, as more and more base gets added. This sharp rise here corresponds to the equivalence point. Now, this is for a weak acid. This is formic acid with sodium hydroxide, which is why the equivalence point is shifted slightly above 8 here. Really, for our purposes, ours is always going to be at the 7 line, okay, whenever we're doing one, because we're doing strong acids and strong bases only for a general class. But it kind of looks like this, where you got this slow, gradual increase, sharp increase, and then a gradual leveling off. And the equivalence point is when that thing goes straight up. And it happens very quickly, right? This happened somewhere between like 46 milliliters and like 48. So within those two, it went from an acidic solution to pretty basic. It happens very quickly. So how do we calculate that equivalence point where we know that the volume is going to be equal from the acid to the base in regards to the concentration? Well, let's read this as an example problem. HBr plus LiOH, acid plus base, gives us lithium bromide and water. 25 milliliters of 0.35 molar HBr solution is titrated with 0.100 molar LiOH. How many milliliters of LiOH are needed to reach the equivalence point? I'm just going to show you the shortcut for this, okay? If it's and the shortcut only works in one situation, which this one does apply. So the shortcut is this equation: MaVa equals MbVb. That's the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And something to note here is this only works if all coefficients in the balanced equation are 1. Only works if all of the coefficients in the balanced equation are 1. Okay, which is the case here, right? There's nothing, so they're all 1, right? How many milliliters of LiOH? Well, that means we're looking for the volume of the base, right? Milliliters is volume, LiOH is the base. So let's rearrange that for VB. Get VB equals MaVa over MB. We can plug in these values here. Molarity of the acid was 0.350 molar. The volume of the acid is 25.0 milliliters. All divided by, okay, molarity of the base is 0.100 molar. Okay, and grabbing a calculator, we got 0.35 times 25 divided by 0.1, and to 3 significant figures we get 87.5 milliliters. Okay, so it's a pretty simple calculation. Really, you could do this also with stoichiometry, but this is the shortcut equation to solve this. Okay, so what happens if it's not a 1-to-1 ratio for all of the coefficients? So here's an example where one of the coefficients is 2. So this question says, if 15 milliliters of 0.250 molar HCl solution is titrated with calcium hydroxide, it takes 45 milliliters to reach the equivalence point. What is the molarity of the calcium hydroxide? Okay, so this time around, we cannot use MaVa equals MbVb, okay? We can't use that because the ratios are not all 1, so we can't use that shortcut here. We have to use some stoichiometry. So the first thing we want to do is convert this volume and molarity of HCl into moles. So to do that, we are going to multiply them together, right? Molarity times volume will give us moles. So that's going to be, molarity is 0.250 molar, and the volume is 0.0150 liters, right? It's got to be in liters. And so that is 0.00375 moles of HCl. We then need to figure out what is the amount of moles of base that is. So we're going to use just a one-step stoichiometry problem here. We're going to have 0.00375 moles of HCl times, okay, we're setting this into, turning this into calcium hydroxide, so setting it up with moles of calcium hydroxide on the top, and moles of HCl on the bottom. That's 1/2, so we'll divide that number in half, and we'll write this with 3 sig figs, 0.00188 moles of CaOH2, okay? And then as far as molarity goes, then we need to calculate that by doing moles divided by volume, 0.00188 moles divided by 0.0450 liters. Okay, and we'll round this to 3 significant figures, 0.0417 molar. Okay, so what about a problem that doesn't reach the equivalence point? One where we don't add enough base to acid to neutralize it, or the other way around, where we have excess of one, either acid or base. The pH will not be 7. So how do we determine the pH in a problem like that? Well, the trick is to first figure out which one you have excess of, okay? because that's going to dictate whether you have extra hydronium ions, making it acidic, or extra hydroxide ions, making it basic. Okay, so to do that, in this type of problem, everything is a 1-to-1 ratio. So what we want to do is figure out how many moles of acid I have and how many moles of base I have. So let's go ahead and start with that. As far as the acid goes, so we'll label this one HCl, right? We have, so it's going to be molarity times volume. Molarity is 0.500 molar. Volume is 0.0523 liters. Let's grab a calculator real quick. 0.5 times 0.0523, and this is 0.0262 moles of HCl. And for the base NaOH, our molarity times volume here is 0.400 molar and 0.0217 liters times 0.0217. 0.00868 moles of NaOH. Okay, so this is the amounts that I've added together here. I've got 0.0262 moles of HCl and 0.00868 moles of NaOH. Now, when these react, they react in a 1-to-1 ratio, and they kind of, you can think of it as sort of canceling each other out. I have extra HCl. So when this is all said and done, I'm going to have extra HCl. And that's going to help us figure out what the pH of the solution is. Then we'll figure out how much we need to add of the base to reach the equivalence point. So let's figure out how many extra moles of HCl there are. Well, it reacts in a 1-to-1 ratio, which means I can simply subtract this number from this number to figure out how much extra HCl there is in moles. So let's go ahead and do that underneath here. Let's label this, let's label this extra HCl. Okay, now this is in terms of moles, right? It's going to be 0.0262 moles minus 0.00868 moles. So 0.0262 minus 0.00868. We're going to round it to the, let's see, thousandths place here. We're going to have 0.017, yeah, 0.01, no, 10 thousandths, 0.0175 moles of HCl. Okay, so this is the extra. We then need to figure out what's the volume, right? In order to get to pH, I need a concentration of hydrogen ions. So the volume is going to be the two volumes added together, since we've added these together, right? It was 52.3 milliliters, which we'll write here as liters, plus 21.7 milliliters, 0.0523 plus 0.0217 is 0.0740 liters. So the concentration, since this is extra acid, okay, of the hydrogen ion or hydronium ion, is going to be 0.0175 moles divided by 0.0740 liters. Okay, so 0.0175 divided by 0.074. This is a concentration of 0.236 molar. And pH is just negative log of that, right? So negative log of 0.236 is going to give us, let's see here, 0.6, we'll call it 0.63. So still very acidic, okay, even after adding 21.7 milliliters of base. Okay, and then we also need to answer the second question, how much more sodium hydroxide must be added to reach the equivalence point? That would be to neutralize it, right, have a pH of 7. Well, I said a moment ago I had extra HCl. I had 0.0175 moles of extra HCl after we subtracted these two numbers. That's extra acid. To get rid of it all completely, I would need the equivalent amount of base, which it's 1-to-1 ratio, so I would need the exact same moles of base, right? I still need 0.0175 moles of NaOH to neutralize the 0.175 moles of extra HCl. So to do that and figure out the volume of the base that I still need to add, we rearrange the equation for molarity for volume, which is moles divided by molarity. And if we plug things in here, the number of moles I need is 0.0175 moles, and the molarity of the base is 0.400 molar. And if we take those and do that division, we are going to get to three significant figures, 0.043, we'll call it 8 liters, which is 43.8 milliliters. So I still need to add 43.8 milliliters to completely neutralize it. Now this is a very long problem. A problem like this might be like an extra credit problem on a test, but an MAVA equals MBVB question will certainly be on there and certainly is within your capabilities. And then lastly, with acid-base indicators, how do you know when your neutralization is complete? Instead of a pH meter, chemical dyes can be used. pH meters are kind of unreliable. You have to calibrate them every time you use them. In high school, pH meters are not super accurate. They're usually close. They'll be able to tell you within a few tenths of whatever your pH actually is, and when you definitely have gone past your equivalence point. But they're not the most accurate, at least with what we can afford. So chemical dyes, though, there's no confusion there. Okay, so what those do, those are dyes that color is affected by the pH of the solution. So when the pH reaches a certain point, the solution changes color. Okay, when that color changes, it's called the end point. All right, different indicators change color at different pHs. Some are, they change color, at 1 or 13. But if you're doing a neutralization with a strong acid and a strong base, you want one that changes somewhere around 7. The most common one that we will see is phenolphthalein. Okay, there's others. There's bromethymol blue, methyl red, methyl orange. There's all kinds of other ones. There's universal indicator, which goes through the entire, basically, range from 0 to 14 and changes color throughout the whole thing. So there are other types of indicators, but the most common one that you will see is phenolphthalein. It goes from clear when it's acidic, and the moment it kind of goes past 7, it is pink. Okay, so when it turns basic. So it turns kind of a neon pink color. So that's a really good one for us to use. It's cheap, it's easy to make, and it definitely changes color right around 7, which is good as an indicator.